Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program.
Now, here's a problem. Oftentimes when we talk to members of the public about colliding beams, it is not clear what we mean by it, why we do it. If you have a particle and you want to study it, why not just grab one, sit down, and study it? Well, there are some technical problems with that. And you could start by making up a list of what you would do if you were looking at a grain of sand. You could pick it up, you could rub it to get some idea of the nature of its surface, weigh it, kick it, stop it, slice it, spin it. Do all the things that we're just used to doing when we are trying to figure out what something is. The problem is you can't really do that with particles that are a millionth of a thousandth of an inch. So we have to come up with different techniques. And one of the favorite techniques these days is to get beams of the particles that you are interested in and slam them into each other and look at what comes out. An example would be a piano. Suppose you had a piano and you couldn't get close to it. Your mother would spank your hands if you touched it. But your job was to figure out how a piano is made. And you're given a list of rules about what you can do. I mean, you can't put your hammer down, put your screwdriver down. You can't use those. But you're told that you could slam two pianos into each other if you wanted to. Well, that's what you would do. You'd slam them together at very, very high energies, and you would find then a mess. White keys, black keys, wood, wire. That made the thing stick together before, but now they're pieces. And your job then is to pick up the pieces and then try to figure out how that piano was put together, maybe even why it was put together. There's some similarity. So we need tools, we use tools in high energy physics, but our tools, our main tools, are just a little bigger than everybody else's. The airport that you see up here, that's the Geneva airport. Faintly, there is a ring, I hope you can see, overlaying there. And that is the tunnel for the Large Hadron Collider. And as you could see, we could drop several airports inside of that circle, and they would all fit. There are many other examples here. A large detector at Fermilab called CDF. The D0 detector at Fermilab. This is Dan Levin, by the way, one of our research scientists at the University of Michigan working in his lab. And this is the tunnel at the LHC, just to give you a sense of the scale of our tools. Now you might ask, why do you need so much real estate? Well, the goal is to get particles moving at very, very high speeds, closely approaching the speed of light. And one way of doing that is to circulate them in a ring, and every time they pass through a point, give them a kick. And these green things here are bending magnets, as shown over here. Particle comes in, its path gets bent to keep it in a circle. The job of the pusher is shown here. Just to get in phase with the particle beam and give it a boost every time it passes by. That's the basic idea of an accelerator. Now, you've heard of the term superconducting, supercollider. What does that mean? Well, you are limited in how fast you can get the particles to go by sort of the strength of your magnet. They have to work real hard to bend a particle a small amount. The bigger the machine, the less work it has to do, because each magnet does not have to bend the beam as much. Well, what's the maximum that you can bend? It's some quantity, but it's limited by the amount of current you can put through your magnet. Well, what limits the amount of current? Well, amongst other things, the resistance of the wire used in the magnet. Now, there's this beautiful effect that if you take certain types of wires, cool them down to sufficiently low temperatures, 4 degrees Kelvin, the wire has a resistance of almost 0. That means for a given amount of power, you can get a higher bending effect. So that's why we need superconducting wire to make a state-of-the-art accelerator. What you see over at this particular slide is an electron beam, and I am going to change the magnetic field that beam sees. All I'm doing is changing the magnetic field through which these particles pass. You see the beam bending? It even curls back, curls back on itself. This just demonstrates that a simple magnetic field can direct the path of a beam of electrons. This is basically a Linic. This is a steel bar. Think of it as a bunch of particles. I'm going to put this steel bar into its accelerator. Then I'm going to turn on a power supply here. And I need to warn you, that little guy is going to come out over here, emerging at a very, very high speed. Well, you might say, why is he doing this? I want to show you that without touching the steel bar, I can accelerate it. And when I said I need to warn you, it's going to make a lot of noise when this guy comes out and hits this steel block. Any other precautions, Warren? Okay. I have 2 fingers, 2 buttons, and I'm about to push it. I'll count down. 3, 2, 1. Okay. So, a bunch of particles can go down a tube, not be touched, and pick up an enormous amount of energy, just because they're alternating magnetic fields, essentially always pulling that bar toward the next section. That's all you have to do is pull it a little from its start, get it going, pull it more, and you get this effect. So you are accelerator experts now. No other, it's just a matter of scale. This is one of my favorite plots of all times. It's been around for a long time. It's the struggle of humankind, or the innovativeness of the human spirit. That's shown here. This is the energy of acceleration. This is the year. 1930, somebody thought of an idea for an accelerator. They built the accelerator. It only was good for a few hundred keV. Then the graduate student in the group says, aha, I know how to improve that. So they made another accelerator of that using this technology. Then another and another and another. Then the folks who were doing this said, have you noticed that there's another technology that our friends are developing that seems to have more promise than ours. Let's stop ours and start using theirs. In the meantime, somebody else has come up with a different idea about how to do it. Over the decades, we kept making better and better accelerators. This is Fermilab outside of Chicago. I don't have the Large Hadron Collider on it, but it's up in here somewhere. But it's the human spirit that's being shown here. You get an idea, you push it as hard as you can. When it doesn't give you what you need, you go to another idea. And in this sense, the Large Hadron Collider is just the onward progression of making bigger and better tools. And by the way, I haven't made the point anywhere else, so I should do it here. We want higher energies because that allows us to look deeper into the components of matter. It's really a general physics maxim that to probe smaller and smaller distances, you need to have probes that are higher and higher energies. So that's the reason we want to keep building bigger and bigger machines. Okay, so here's the LHC. These are smaller accelerators at CERN in Geneva. In the end, we want one beam of protons going in this direction, another beam going in the opposite direction, colliding in the middle of each of 4 detectors. Around a detector, you build a small campus. In Geneva, this is 27 kilometers around. It's buried under the French-Swiss countryside. There's a bunch of particles being accelerated from smaller accelerators to larger ones, and then eventually dumped into the big ring right there. In the meantime, other bunches are being prepared to go in the opposite direction. And here are 2 particles about to collide inside of the Atlas detector, and there's the result. You can imagine the technological challenge of sending particles around a 27-kilometer ring, timed so that they arrive back at one of the detectors at exactly the same time, going in opposite directions. So how do you detect particles? You know, I've told you how we can spin them up to high energies. Here's an example of a scheme to detect the passage of a particle. If you have a tube, let's say the outside is kept at ground, and it has a wire down the middle at a very high voltage, and it's filled with some gas, let's say argon. When a particle passes through, it ionizes the gas. These charged entities see an electrical field causing them to drift to the center of the wire. Electronically, when you see a pulse on the wire, and you know how long after that is, the passage of the particle has occurred. You then get a measurement on where the particle passed. What you see here is an example of a set of drift tubes built here in Ann Arbor. Otherwise, why would the stand be blue? Fabricated here and then shipped to Geneva for inclusion in the Atlas detector. There are various schemes that we have for determining what kind of particle just passed through. Either a tracking detector that just sees the tracks, or electromagnetic calorimeter that allows us to see electrons and photons. Hadrons would stop in this set of detectors, and anything that makes it all the way through to the outside is very likely a muon. And the Michigan group actually spent most of its efforts looking at working on muon detectors. I just have to show this picture. There was something called a predecessor of the electronic readout systems like drift tubes was the bubble chamber. This is what a bubble chamber photograph might look like. In this case, it's a kaon coming in, striking a proton in the liquid, making another type of particle that travels some distance, and then decays into a pi plus and pi minus. Now, you might say that's nice, but why is he taking time to talk about something that's 25 years old or more? Many reasons. One of them is that the inventor of the bubble chamber was Donald Glaser, who was here, and he got the Nobel Prize for that development. Several decades ago, this was the workhorse for finding particles. This is how we used to do experiments. We take hundreds of thousands of photographs of the bubble chamber. What is a bubble chamber? It's a device, you put liquid into it, you bring the liquid almost up to the boiling point, but not boiling. Then if a particle passes through, you get local boiling along the path of the particle. And as the bubbles start to grow, you stop it, you photograph it very quickly. And that's how you end up with hundreds of thousands or a million photographs. With a graduate student or hired help to scan each of those photographs and put information into a computer for analysis to look for particles and events that you've never seen before. This is the standard model in high energy physics at the moment. So what do we think we know? We think we know that there are 6 quarks. There are 6 leptons. There are these carriers of the force, photons, gravitinos, Z and W bosons. And that's it, ladies and gentlemen, basically. Any question you have for me, I can answer it by doing various hand waving and pointing to this chart. Now, let's test that. Almost everything we know, I mean, the normal matter is made up of up quarks, down quarks, and the leptons. One of my old professors, and a dear colleague of some of you here, Marty Pearl, discovered the tau lepton, got the Nobel for it. Charm quarks, the C quark, that was discovered by Sam Ting, an old office mate of mine in Randall, in the basement of Randall, back as graduate students. A student of Professor Larry Jones, who is in the audience here today. And Sam was given the Nobel By the way, the electron was only discovered in the late 1800s. Only. And then a long time went by before we discovered the proton. These things are not from biblical times. It's very recently that we started to understand the nucleus. You know, the proton and neutron are the constituents there. And then 1932 only that we discovered the neutron. And then we limped along every decade or so finding new particles. But then all of a sudden, this large number of particles that seem to have nothing to do with each other. Physicists do not like that. They think nature has some simplicity in it, and things were just getting out of hand. Well, that's where quarks come in. Because with only 6 quarks, and they're antiparticles, you can make anything that we know. Proton, what is it? It's 2 up quarks and a down quark. Oh, you said you didn't want a proton, you wanted a neutron? Well, it's an up quark and 2 down quarks. And this list goes on. Pions, kaons, and what have you. They can all be made up from these elementary quark particles. If you start off up here and talk about a cell, that's its size in meters, or in microns. You look inside the cell, what do you see? You see, you may see strands of DNA. Quite a bit smaller, but that's what it is. What is this made up of? Well, it's proteins, molecules. Well, what's inside of a molecule? Atoms. Well, what's inside of an atom? Well, except for the electrons, we have protons and neutrons. Well, what's inside of protons and neutrons? Quarks. Now, I should stop here, and there are a couple of interesting points. One is, you wouldn't be surprised if I told you that one of the questions out there for us to look at the LHC is whether quarks have anything inside of them. And what is this progression? It's entirely possible that whatever you look at, there's something inside of it. But you might also reach a point where, no, that's it. This is the last frontier. And of course, we're very, very eager to get some insights into this. When the Big Bang occurred, there were huge numbers of these fundamental particles created. And astrophysicists, cosmologists are very interested in knowing how they might have interacted during this very early period, maybe a second after the Big Bang. And one way to get insights into that is to look at particle interactions at the LHC. So that's another area of deep interest. Okay, major scientific challenges. I've already mentioned these. Another very interesting point is there something called supersymmetry? And I'll say a couple of words about that. Is there evidence for extra dimensions? I probably will not say anything more about it, so let me take a second to tell you what it's all about. How many dimensions do we exist in? Now, if you ask that question to most people, they will say, well, surely, you know it's 4. You give me X, Y, Z in time, I can tell you exactly where we should meet for dinner and at what time. No confusion. But is that, as Peggy Lee used to say, is that all there is? We don't know. There could be many other dimensions, and we just do not penetrate or interact with those dimensions. I often tell the story of blind fish in Mammoth Cave in Kentucky. Kentucky is my home state. And as you know, there are little streams running through some of the caves there in which blind fish live. And they spend all their life going back and forth in this dark cave on a little stream. If you were to interrupt one of them in their daily journey and ask them the question, how many dimensions are there? I'm not sure they would say 4. They don't know anything about X, Y, and Z. Instead, they probably know just about S. They can tell where they are by telling how far they are from some given point. Could we be in a similar situation where we're actually living in 10 dimensions, but all we really see is 4? Well, we have, in principle, ways of testing that. We can calculate the rates of certain particle interactions, and if they are off from our calculations, one possible explanation is that there are more dimensions than we know about. The Higgs boson is predicted by the Standard Model, the only particle predicted by the Standard Model that we haven't been able to find. And finding it is extremely important. If we can't find it in the mass range where we expect it to be, then that could be a real challenge for the Standard Model and our understanding of particle physics. So many, many groups are focused on searching for the Higgs. In the common literature or magazines and what have you, you often hear reference to the God particle. And that's the Higgs, because it would be the particle that essentially determines the mass of all other particles. So it's of a level of interest far beyond that of a typical particle. It's very hard to explain the Higgs. So people come up with novel techniques for trying to convey what the Higgs might do. Suppose all of those people at a party represent the Higgs field, and that it fills all of space. And that something unusual enters, someone unusual, enters the room and starts to walk across it. And that he has certain features that draw the attention of all of the occupants of the room, starts to walk across the room, people coalesce around him, and he finds it hard to move. Well, being hard to move is what we call mass, right? Have a given force, the rate of your acceleration is determined by the mass. So the field impedes the motion, gives the particle mass, and that's one way, non-rigorous way of looking at what the Higgs can do. Finding the Higgs could be a real challenge, though, experimentally. We know that one of its decay modes should be into 2 gamma particles, two photons. So when we do the experiment, we can look at each event that has 2 photons in it. Then we can ask the question, what would have been the mass of the parent if these 2 photons came from, say, the Higgs? You can do the calculation. By the way, this is a simulation of what you might see. It may be only this little bump right here that leads to the discovery or claim of discovery of the Higgs. But you see the job the physicists have. They have got to pick out little bumps like that over a huge background. And those of you familiar with statistics know that there's some probability that fluctuations like that will occur even when there is no particle. So that's a little insight into the Higgs situation. I'm going to skip this about symmetries, although it's very, very exciting. Supersymmetry It's an area, by the way, that Michigan theoretical physicists play a huge role in. This would be a symmetry between fermions and bosons, particles with half-integer spin and particles with integer spin. And it has a lot of interesting possibility. It might even explain dark matter. We only know some small fraction of the mass thought to be in the universe. The other is not seen. It's called dark matter. SUSY could accommodate that. SUSY predicts many new particles that have never been seen before. Why haven't they been seen before? Because we've never had an accelerator with enough energy to produce them. And so there are other groups in the experiment that are going to be looking for SUSY. Okay, so we're finally getting to CERN. CERN is the European Laboratory for Nuclear Physics, located near Geneva. It's an organization right at the time that has 20 member states. Here they are. We are not there. You will not see a US flag. But we do our experiments there. We're visitors. We're well-treated visitors, but we're nevertheless not part of the CERN management. Many dignitaries come to the lab regularly. This is a very nice photo taken of the visit of Pope John Paul many, many years ago. In a given month, there are dignitaries, presidents of European countries, and so on, who come to the lab. I mentioned before there are 4 experiments around this 27-kilometer circle. CMS, compact muon solenoid, ALICE, ATLAS, and LHCb. This is all 100 meters underground. And there are cows grazing above the ring. One of the things that's been very remarkable to me is that the French and Swiss would so warmly give up or give the rights to put this huge monster underneath their farms and countryside. This comes from my colleague, Professor Bing Zhou, who used this to show the energy of the accelerator. 14 trillion electron volts. And in order to envision this quantity, think of a trillion, well, think of a battery for every star in our galaxy, put in series. This is some details. Well, I've already mentioned to you that we have bunches of beam of protons going in counter circulating directions. Here's a bunch, here's a bunch. One proton in that bunch, one proton in that bunch. They collide. But really what's happening is that the quarks and gluons in them are colliding. And they can produce things like the Higgs. What we see is the final state products, and then we have to infer whether or not a new particle like the Higgs there. Gives you some idea of the ring, underground, 100 meters, 1,200 magnets. It's really impressive. It's a feat of human engineering. Collaborations are huge. That brings their own set of problems. This is an example in Building 40, where one day someone said, all of you that are here over lunchtime, please come out and look over the balcony and we'll take your picture. And I'm going to have to highlight myself because I keep having trouble. I'm going to go into Photoshop and enlarge it. But this is a fraction of the individuals working on Atlas that just happened to be at CERN at the time this picture was taken. I'm going to go through these. I've already talked about Atlas, maybe a little more. There are segments and layers of the detector, pixels and what have you, in order to detect particles that are produced at the collision point, and then electromagnetic calorimeters, and on the outside, the muon detectors. And the University of Michigan played a major role in building the INCAP muon counters. A little bit of history. People have been working on the Atlas experiment for a long time, well over a decade. And there are various milestones. Speaking of Photoshop, this gives you some idea of what of the size of the Atlas detector placed in the Michigan Stadium. Here are the universities across the US that are participating either in the big compact muon solenoid experiment or Atlas, red or blue, and you can see them. A very significant number of major US universities are involved. But as I mentioned, the University of Michigan has the largest number of collaborators. Worldwide, this is the situation. The number in the US has now really risen up to over 900. You see Europe and South America and China. So it's truly a worldwide event, collaboration. Having a meeting is very difficult. Even by video conference. It might be 9 o'clock at one point, a wonderful time to have a video conference, but somewhere else your colleague is, it's 3 a.m. in the morning. So collaborative tools and some thought about collaboration is very important. Take a look at Atlas. You can see what fraction of the role in terms of number of authors. USA is the biggest single country. CERN has many, it enters as an institute. England, Italy is quite large. And here is the balance for the other experiment, CMS. But the US is playing a very major role, in spite of the fact that we're not a member state. Computing at the LHC is a huge challenge. We will be generating tens of petabytes of data per year. Peta means 10 to the 15th. So, it's 1,000 times a million times a million bytes. That's the equivalent, or will be the equivalent, of almost 1 million of today's PCs. So we're tackling a data management problem that nobody has ever tackled before. Not the military, not NASA. And the concept that's emerged is grid computing, that essentially ties together huge numbers of computers across the world so that they can be deployed to help us with our analysis. You can just look at that blue picture, blue and red on the right, and get some idea as to how hard it is to do the analysis. You've got to pick out of all of that junk a Higgs boson, which actually is hiding there and shown by the lines there. So the computing challenge is awesome. This is an example of the computer cluster at CERN, but only 1/3 of the computing will be done at CERN. The rest of it has to be done at universities. This is the scheme that is used to distribute the computing workload. Here's the experiment. It goes to a tier 0 in Geneva, gets fanned out to national centers. In the case of CMS, it's Fermilab in Chicago, where data then is shared with a collection of tier 2 centers, and then the tier 2s service individual small universities. Michigan is a tier 2 center for the ATLAS experiment. And so we interact, and for us, this is Brookhaven National Laboratory. We interact directly with Brookhaven that gets its data from CERN. So just the tiered nature of doing the analysis is a challenge. The speed of networks is greatly outstripping the speed of computers, the growth in the speed of computers. That's why something like the grid makes sense. In other words, if I have $1,000 where I could buy another computer and estimate how that would help me with my research, as opposed to taking that $1,000 and getting better network connections, it's probably better for me to invest in the network. Because, just to give an example, in this period, the speed of computers may go up by a factor of 60, speed of networks by a factor of 4,000. So it's better for me to take my computer and tie it to yours than for me to go out and buy another computer. And that's what the grid makes possible. By the way, this is a little serendipitous note. There is a particular experiment that I'm interested in, and we've been working on trying to get ready for it over the past few years. We needed some new information about a particular parameter, it's called alpha, so that we could look at the polarization of lambda b hyperons by examining this particular decay. The information we needed was not available. It's hard to estimate the rate, our precision, without knowing the answer to another question, which we thought was buried in data at Fermilab. So I asked our postdoc, Edward de la Cruz Borrello, to go to Fermilab and try to extract enough information so we could estimate alpha for the lambda b. He did that, and in the process, created a data sample inside of which we were able to discover a new particle just last year. It's called the Chi-B. There's the peak that we observed. I don't have time to really explain the details. And more recently, mining that same collection of data, we discovered the omega b. So I should point out that the key people involved in this were Edward de la Cruz Borrello and Professor Jianming Chen. We were extremely excited. You normally don't have a chance to discover new particles. And this is a B quark, a U quark, and an S quark. It's a quark from each generation. It's one of those combinations that I told you should exist, but nobody had ever seen it before. Okay, here are the people at the University of Michigan that have been involved. Really a top-flight group. Faculty, postdocs, research scientists. This gives a list of the specific Michigan role. This shows chambers that we made across the street being loaded into trucks for shipment to Geneva. Here are individuals working in the assembly room. We have a huge granite table in the basement of the physics building across the street, or not basement, but ground level, on which the chambers were made. Granite table, extremely important for it to be perfectly flat. members of our group in the pit, in the Atlas experiment, the arrival of Chambers in Geneva. And by the way, the Chambers, the little stand you see over here is a scaled-down version of Chambers. It was assembled by Dr. Dan Levin, Curtis Weaverdyke, and undergraduate students here. If we have ideas of new things to test and try, even while the experiment's going on, we could do it here. And then if we find improvements, we can even inject those improvements into upgrades for the detector. More students working here on Chambers. More work on Chambers in the building across the street. Education and outreach. I mentioned the difficulties of collaborative tools being needed to keep everybody posted on what's going on in the experiment. Here's an example of the spokesman for the Atlas experiment giving a talk in Bern last summer, which our people recorded, put on the web immediately thereafter. These are the slides that Peter Yenny was showing. So we all can't go to all meetings every time, but we can rely on strong collaborative tools to try to keep abreast. By the way, there are 2,000 physicists in the Atlas experiment. We have a big meeting, maybe 300 of us can go in a particular meeting. But the other 1,700 or so badly want to know right away what happened at that meeting. And so this is actually a Michigan-developed scheme for making web lecture recordings. We also have developed a remote teaching facility. It is very, very difficult to teach here and do your duties in Geneva. Every now and then, we get to stay an extra couple of days by giving your class from Geneva, giving your lecture, back to students here at the University of Michigan. You have all the tools you need, you have a whiteboard you can write on, you can show your slides, and you can hear your students when they stop you and ask questions. We recruit and take to CERN every year about 15 undergraduate students. We recruit nationally, and they go to Geneva. This is a program that I help administer with Professor Jean Krish. Jean is here, I saw her. And we're funded by the National Science Foundation to do this. We view it as part of our responsibilities, but also it's a lot of fun. These are some of the brightest young people in the United States. Here they are in Geneva. There was a cultural component. The kids get to travel from Geneva on weekends. We socialize a few times during the summer. But most of the work is the students working directly with a mentor who may be from Greece or Italy or Russia. The students give their lectures on the work they're doing once every 2 weeks or so. We added a component a couple of years ago to bring teachers into the program. 5 high school teachers come to Geneva to participate in lectures. I should also mention, I did mention Jean, I should also mention that Myron Campbell, our chair, has been deeply involved in both the REU program and the RET program, and came over and spent time getting the program launched, for example, in June. Tim Berners-Lee, web development, Geneva. I think this is just an example of what can happen when you get a bunch of bright people together. Basically, he was asked, Tim, can't you do something to help us exchange files more efficiently? And he said, yes, sir, and went off in the corner and developed this little thing, which is now turned into the World Wide Web. There are spin-offs to society, proton radiography and other activities that had their origins in high-energy physics. This whole area of superconducting, where we were not the ones who discovered superconductivity, that was done by colleagues in solid-state physics. But we did provide this huge challenge of how do you get hundreds of miles of this kind of wire. How do you manufacture it? Startup challenges, a huge amount of excitement on September 10th, 11th, as beams were first circulated in the collider. Not collided, but circulated in each direction. That was a milestone. The intent was not to collide beams until a few weeks later. But unfortunately, well, first let me show you the excitement. It's pretty much like being at NASA when there's one of the successful space launches. Now, but unfortunately, I'm going to get to an incident that happened a couple of weeks thereafter. But first, I should tell you that there's been a lot of interest in stories that we were going to create black holes. And it's so interesting to see the public assessment of that versus that of the physicists. The physicists are hoping that we can create black holes. And there have been papers hoping for that for some time. But these are really different things. These are mini black holes. This is a simulation of what's expected for one of them. This concept of the Hawking's radiation plus other considerations really, to us, make it very, very improbable that anything bad will happen. And I notice Fred mentioned that Frank Wilczek will be here. He's sort of an expert in this area. Probably will talk about it during his talk. Here's the incident. You may have a little trouble reading it. It just came a couple of days ago. I copied it down. This comes from the Director General of the lab. There's been an assessment of what happened on the 19th. The accelerator probably will not run again until next spring, coupling with a planned shutdown. There are enough spares to replace the damaged magnets. It is still not known in detail what happened, except it seems to be due to a faulty connection between two magnets. The whole tunnel, all the magnets, in order to be superconducting, have to be kept very, very cold. And there's a large amount of helium gas involved. There was a rupture, froze a section of the tunnel, and for a long time, the technicians couldn't even get to the part of the tunnel that was damaged to assess what had happened. But here's the Director General saying there are enough spare parts, and describe some of the work that's going to be done to make sure this type of problem doesn't occur again. But as you can imagine, the excitement of the staff at the lab was badly damaged by the roller coaster news. First excitement for turn on, and then great disappointment because of the incident. But I should also tell you that there was even a component of the staff at the lab who were quite happy. They were going to have some extra time to get ready. Okay, national science policy issues. And what are the implications for having the world's largest basic research laboratory outside the US? For students, it's not good. It's not easy to get your graduate students, certainly not undergraduates, to Geneva. There are 90 US universities involved at the Super Collider, at the LHC. We can only bring in our program about 15 students over each summer, and that's it. A few more come with groups that are doing work, but like I say, only one out of every a very small fraction of the 90 universities get to send one student. So it's not good for students to have to go to Geneva to see a running high-energy physics experiment. For faculty and researchers, there are great challenges in having to teach your classes while also discharging your responsibilities in Geneva. And for the public, it's not been good either. I was on the board of overseers of the Super Collider. And I watched the interest of states like Texas in having the Super Collider brought to Waxahachie. As a matter of fact, Texas gave us, I think, $1 billion. You might ask, why would a state on its own give you $1 billion to help bring something like the Super Collider to its area? Well, it's because they recognize the potential impact on the school systems and throughout Texas. To have such a facility where you could bring grade school kids in had some value. We won't have that option if the only accelerators are offshore. Last slide. The Large Hadron Collider is one of the most significant scientific instrumentation advances in our generation. It's very, very likely that we are going to know a lot more about particle physics, the evolution of the universe, and other topics once we get that machine up and going and collect enough data over the next 2 or 3 years. And I just want to close by really giving a tribute to the members of the Atlas group, and to indicate that I think the citizens of Michigan and of Ann Arbor should be very proud of that group. I won't even try to mention their names because I'll leave someone off, but it's a spectacular group, major efforts by Professor Bing Zhou, Jay Chapman, Rudy Toon, Dan Amadei, Xianming Chen, and others on the faculty. So I should stop here and see if there are questions. Thank you very much.
Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program.